好，同学，那我们开始上课。So we will start our class on detection and estimation. So as we said, uh, detection deals with the discrete type of problem, and while its estimation deals with the continuous type of problem. So we will first look at the detection theory, and then at the first half of the semester, and then estimation for the second half. Okay, so let's first take a look at the applications. The applications of detection includes radar, uh, communications, speech, and sonar, image processing, biomedicine, control, seismology. So I think it's obviously that radar system. No, I'm sorry. The radar system is trying to detect the speed, location, and coordinate of the target, and then communications, PSK, QPSK, so on and so forth, and then speech. Speech is detecting the waveform of people's speech corresponding to which vocabulary. It's trying to translate the speech into the vocabulary. And sonar, of course, is the underwater detection, and image processing, trying to detect whether or not there's an object. For example, is there a dog in the image, or is there a bicycle in the image, and things like that. And biomedical deals with either effective or not effective. So if for example, if a medicine is created, then it's effective, effective, or not effective. So that's the question about biomedical. And then control system is trying to, of course, if you want to control a aircraft, you need a lot of detections. Detect its altitude, detect its height, detect its speed, and things like that. The speed of the wind. And seismology is detecting the center of the earthquake, or the magnitude of the earthquake. So that's the detection. Okay. So mostly I would follow the textbook to do this lecture. So you can also follow, for example, this is a page number, and we're just going to go through, but some of the subsections at the end of the chapter will be skipped. Okay. So, so if so, this is uh, the hypothesis testing problem. For a detection problem, there is a formula that's called hypothesis testing, and also the decision theory. Later on, we are going to talk about its mathematical formulation. Okay, so this PSK example that we have talked about, the transmitted signal is either a 0 or 1, 0 or 1, and then the receiver is trying to detect, is the transmitter transmitting a 0, or is it transmitting a 1? And then the modulator converts a 0 to the waveform, this waveform, or convert 1 to this waveform. As you can see, this is a cosine 2 pi f0t, and this is minus cosine 2 pi f0t. So the difference is plus 1 and minus 1. That is a very good correspondence to plus 1 or minus 1, or in this case, it's denoted by 0 or 1. Denoted by 0 or 1. Okay, so here is let's look at the figure example. If there is an aircraft, then it is transmitting a waveform. This is a transmission of the waveform. And after a while, the waveform is refracted back. As a result, you can see this waveform being transmitted and this waveform being refracted. But when it's refracted back, it actually is distorted. As you can observe, it's distorted. It has noise and distortions. So all those things will be different from, the sinusoidal wave that ideally we are expecting. But there will be distortions. And also, if there is no aircraft, you will receive just this noise. So this is the same as the noise here. And then this is the major waveform that's refracted back. Okay. And this is a digital communication problem. You have a digital source and it transmitted 0 or 1. And the modulator would generate either S0 or S1. And that is cosine and cosine plus pi. It's phase difference by pi. But the phase difference is refracted as, it's like +1 or -1. If we recall, it's something like here. It's +1 or -1. You have a minus here. If it's a pi difference. Pi difference is 180-degree difference. And then the noise is added. And then it goes to bandpass signal, demodulator, and detector. So let's see if 1 is sent. The 1 is sent. Then ideally you are expecting something like that, right? This is an ideal case, but as we say many times, it's disturbance and noise, so it couldn't be that perfect. As a result, you get distorted signal, and -1 is the same thing, -1, and it gets distorted. Okay, as we say, if there's a noise, then we are happy, but we're out of business. Okay, so this is the +1 -1 communication, digital communication. And for speech, this is a pronunciation of a vocabulary 0 and 1. So you pronounce 0, 0, 1, and then you get waveform like this. Okay, so you can see that it has a sequence of waveforms. And then the challenge is how do we translate that waveform into 0 or 1, right? That's a challenge. Just by visualizing the waveform, we would not be able to distinguish. So it would actually require a very sophisticated system for detection. And then this is the same. It's the utterance of a certain vocabulary. Okay, so yeah, so we have shown some examples. So okay, so then let's go to page 7 and then describe in more detail what happens. Okay, so usually when we see a waveform, it's just a waveform. By visualization, we will not be able to do anything. So we need to take data. So it's a discrete time data set. Okay, so mathematically, we assume that the endpoint data set of the data are x0, x1, all the way to -1, and make a decision based on its value, right? You have a sequence of waveform. Imagine how difficult it would be if you just visualize it. Then the thing is, we need to take samples. For example, we take samples. at a discrete time and take multiple samples. So this is x1, x2, x3, x4, x5, so on and so forth. You can take many samples. And based on those samples, we are to make decisions. So that's called detection theory. Detection theory. The observation of a time series is a discrete time process. So our problem now evolved to a decision making based on data, which is a statistical hypothesis testing. Okay. Then the detection problem. The simplest detection problem is to detect whether the signal is present, which as always is embedded in noise or if only noise is present. An example of this problem is the detection of an aircraft based on radar return. Radar return. Since we wish to decide between two hypotheses, signal and noise versus noise only. So this is to say the aircraft example. If the transmitter transmits the signal and the aircraft is present, it will refract the signal back. So you see the signal. If there is no aircraft, then the signal will go out and disappear. As a result, you will see no refraction. No refraction. So that is the decision making for target present that we call target problem. Target problem. Meaning whether or not the target is present or not present. So we turn this as the binary hypothesis test. How come it's binary? Because if we just imagine there is two hypotheses. One is the target is present, and the other hypothesis is the target is not present. So that is called hypothesis test, but a binary version. Of course, then it can always be generated to the multiple hypotheses, more than two. But currently, we talk about two hypotheses. Okay, so it also here we also frequently occurs that we wish to decide among more than two hypotheses. In the speech recognition example, our goal was to determine which digit among the 10 possible ones was spoken. Such a problem is referred to as multiple hypothesis test problem because we are essentially attempting to determine the speech pattern or to classify the spoken digit as one of the set of possible digits. It is also referred to as a pattern recognition or classification. Okay, it's a kind of the same thing, the same mathematical structure in different kinds of domains. Sometimes people call it pattern recognition. Sometimes people call it classification. But no matter what, it is the same problem. You are deciding one of many. Remember, one out of many. So, for example, you will pronounce 1, 2, 3, 4, up to 10. You are choosing one vocabulary out of the 10 possibility. So that's the multiple hypothesis test problem. And it's statistical. So because of the noise, because of the uncertainty, so it's a statistical hypothesis test problem. Okay, so now we go to 1.3. 1.3. The mathematical detection problem. By way of introduction, we consider the detection of a DC label. DC label is a very common problem. A equal to 1 embedded in Y Gaussian noise Wn with variance sigma square. To simplify the discussion, let me eliminate that so that it's easier to see. Okay, so it's a equal to 1 embedded in Y Gaussian noise with variance sigma square. To simplify the discussion, we assume that only one sample is a variable on which only one sample is a variable on which to base the decision. Hence, we wish to decide between the hypothesis x0, w0, and x1 equal to 1 plus w0. So this is one sample, meaning that you're taking only one sample. Then this A is the so-called DC. That's a DC, meaning signal in noise. Signal in noise. So since the noise is assumed to be zero mean, we might decide that a signal is present if this, right? Signal is present. This is one of the hypotheses, right? Noise only is another hypothesis, right? Hypothesis with signal, hypothesis with noise only. Okay, so what that means is if you have this x0, it's either noise or signal plus noise, then how would you distinguish by this observation? That's the challenge. That's the challenge we have. So if we draw a line, it's either noise, right? Noise, or 1 plus noise. It's going to be around 1, but it's a bunch of noise around 1. So the way we distinguish is we cut in the middle. We cut in the middle and then say, hey, if it's more than 1/2, then we say this hypothesis. If it's less than 1/2, we say this hypothesis. So that's basically these two equation is telling us. Then since expected x0 is 0 if noise only is present, and expect x0 is 1 if a signal is present, then the decision of path can be arbitrary, right? If it's just a coincidence in the middle, we can take the decision to be arbitrary, but the probability is very low. It's very low. It's close to 0. Okay, so in reality, we don't really need to worry about this. Okay, so clearly we will be in error whenever a signal is present and then W0 is smaller than half, right? Or whenever noise only is present and W is larger than half, right? So this is to say, how will we make errors? How will we make errors? If hypothesis, if the noise only, for example, in this case, and you have a noise that is large, then it goes to another area. You are mistaken this hypothesis to this hypothesis, right? That's the one type of error. The other type of error is if this is the hypothesis and the noise is too small and then it goes to another hypothesis, you make a mistake because you are making this hypothesis and your decision is this hypothesis. Okay, so that is the error we're making. Hence, we cannot expect to make a correct decision all the time. It's very important. We are not expecting correct decisions all the time. Hopefully, we will decide correctly most of the time, but we try our best efforts in doing that, but we don't guarantee that. This is the core business of detection. You always reserve the possibility of making an error. So, so a better understanding can be obtained by considering what would happen if we repeat the experiment a number of times. This is to say that we observe x0 over 100 realizations out of that when the signal is present and when it is not. Then some typical results are shown in here. Okay, so we will see the figures later on. We'll see the figures later on. So let's go to see the figures. Realizations of realizations of x0 for signal present and signal absent for this sigma square. Okay, so if you have a noise that has a deviation, right? It has a variance, and the variance is going to deviate a bit, right? It's, supposedly it's 0 in the middle, but uh, since it has a standard deviation sigma and variance sigma square, so each time you realize it, it deviates a little bit. It deviates this way or that way, this way or that way, depending on randomness. It's actually a randomness, so we don't really control how it works. It's just randomized. And if you have a signal 1, it's going to be centered around this 1, right? And again, you have a noise, so it's randomized. Going back and forth around that area, and this is going back and forth. And if you have a larger signal, uh, if you have a larger standard deviation 0.5, it's going to deviate more than this one, right? It deviates more. It deviates from 0, deviates out, okay? Rather than this deviation, it deviates a lot. Okay? And let's take a look at the histogram of this and sigma for two different uh, variants. You again see it's 0, but it deviates, right? It deviates around the area. And this is 1, and it deviates, right? If that is larger, 0.5, then you see that it deviates a lot, right? It deviates a lot. For this 0, it deviates a lot. It even covers a lot of probability, even covers up to this 1, right? And for signal plus noise, it also deviates a lot. And as you expect, it's going to make a lot of more errors, right? It's going to make more errors. The reason is it covers the range of the other hypothesis. The zero hypothesis, outcome of the zero hypothesis covers to the range of one hypothesis, right? So, but up to this point, we are still visualizing it. We haven't done the mathematics yet, and we're going to do that. Okay. So yeah, so let's take a small break and come back later.